Okay, well, sorry I didn't get these things posted Sunday morning, but it is Saturday at 5:38, and I'm about to give you section. I'm going to do a little review and then move on. So little 8.4 and 8.5. Posted later than usual, but I'll get these done and get them started loading. I'll also load them in a lower size, so the quality won't be probably as good, but you should be easier to download and access. Okay, here we are. I am recording 8.5 now. I'll also record 8.6 and 8.7. Looks like we'll also do this in school on Monday because the snow prediction is much reduced from what it was originally. But I'll do 8.5 now, 8.6 and 8.7 I'll have ready because we probably won't have time to do them all on Monday. Tuesday we'll review, Wednesday we'll take the tests. So here is, I'm going back to, this is example 4 from, I believe it's 8.4, arithmetic series. Series is the sum of the terms in a sequence. This is a lesson that Jeff taught while I was gone to the board office. So here you go. I put the solutions up here. I think you did these in class, so I'm not sure what you did, but I at least put the solutions here. If you need to freeze this page and look at what I did, go through the sigma, get the first several terms, and then either add them up, and you can see some of them went to a second line, or get the first few terms, get a pattern, identify that it's arithmetic, get your first term, get your D. Some of these subscripts are messed up, and then plug them into your formula to get your answer. Okay, so then I'm going to go on and flip through these fast. If there's a page you want to look at, an additional example or something, go ahead and stop and look at it. But what you want to do right now, just for these, if you feel like the practice is good for you, stop it, look through it, and then compare your answer. Again, in each case, now we're asking ourselves questions, and the questions are, is it a sequence or is it a series? A sequence is a list of terms that follow a pattern. A series is the sum of the terms in the sequence. And then you are going to identify A1, D, and N, or what things you know. Use the formulas on your card. The first formula on the left side of your formula card is explicit formula for an arithmetic sequence. The following two formulas are the formulas for series. One if you have the first and last term, and the bottom one for if you only have the first term, D, and N. You can also, of course, solve for D or N or the first term if you have the result, either the last term or the result of the series, the sum of the series. All right, so if you want to practice these and compare these answers, then I'm moving to 8.5, geometric series. Arithmetic sequence is when you add the same, or you could add a negative number, same number, and so it goes up or down by the same amount, same number. Geometric series is when you multiply by a common ratio. So that's a geometric sequence. A series, so hard to keep the S's straight here. Geometric series are sums of consecutive terms of a geometric sequence. Can be evaluated if you know the first term. That should be first. FI got left out there. So if you know the first term, and the common ratio. First term would be written as G sub 1, common ratio would be written as R. So we're going to evaluate geometric series. We're going to use geometric series in real world situations. I'm going to roll this up. We're going to advance. Geometric series is an indicated sum of the terms in a geometric sequence. As you add them up, you call a certain sum of terms a partial sum. So when you have just the first term, you have the first partial sum. When you're adding the first two terms, you call that a second partial sum. When you're adding the first three terms, you call that a third partial sum. And then when you add all of them, but it is a finite number of terms, that it is an nth partial sum. So if you're adding 15 terms, that would be the 15th partial sum. Okay, here's an old legend. A story is told that the king of Persia, after learning how to play chess, offered the game's inventor a reward. Clearing a chessboard, the inventor asked for 1 single grain of wheat on the first square, twice that on the second square, twice that again on the fourth, and so on for the whole board. The king, ready to give jewelry, gold, and other riches, thought that this was a modest request, easily granted. Was it? The king was not very mathematical. So let's write the sequence. Well, on the first box, he has 1. Then he has 2. Then he has 4. Then he has 8. It doubles, 16, 32. As you notice, these are powers of 2. So 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on. So since we started with 2 to the 0, by the time you get to the 64th block, it's 2 to the 63. Take a second and type that value in your calculator. Big enough number for you? Okay, now we're going to write the sequence. So we have it down here. I'll write it up here. 1, 2, 4, 8, 16, 32, 64, and it continues doubling the first 10 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 5, 6, 12. So I'm sitting here in my living room, don't have my calculator out, don't have the cards, so double check anytime I say a formula and make sure it's correct. All right, now you sum those first 10 terms. Okay, now we want to sum the first 50 terms. Remember the story about Gauss, as you would line them up, you'd have 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 all the way up to 2 to the 63rd. Then you line them up the other way, 2 to the 0. By the time you get down here, this would be 2 to the 63rd. So 2 to the 62nd, 2 to the 61st, 2 to the 60th. And what do you notice? In each case, you add to it 2 to the 63rd, so you have that whole thing lined up. Okay, let's go to the next page. So here you have it lined up. Now this time we're going to write 2 times s, so it's a tad bit different. Why? Because we want all powers of 2. So now we're going to go, the first series is 1, 2, 4, 8, as you saw on the page before. 2 times that series, 2, 4, 8. Now we're going to do the first row, subtract the second row, but we're going to subtract this way. So we line them up, each of these subtract, and the result is 0, but we had nothing to subtract from 1, so that 1 becomes this 1, all the others subtract, and then the last thing left was this, and you're subtracting it, so minus 2 to the 64th. So we have minus 2 to the 64th plus 1. By doing that, we have this answer, but if we had doubled it and subtracted the other way, we'd end up with we'd end up with 2 to the 64th minus 1, or aka multiply by negative 1. 2 to the 64th minus 1. Okay, let's look at this in a more general sense. So here, we used 2 last time because that was r. So we have g sub 1 times r, g sub 1 times r squared, and that's the way all the terms get generated. Here, if you multiply through by r, Now you have g sub 1 times r, so g sub 1 becomes g sub 1 times r, and such. Again, we subtract. All of them cancel down, or not really cancel, but you subtract them and you end up with 0, except you have g sub 1 left, and you have subtracting g sub 1 times r to the n. So g sub 1 minus g sub 1 times r to the n. Factor out g sub 1. Here, you have g sub 1 times 1 minus r to the n. Here, factor out s sub n. You're left with 1 minus r. Now we're going to divide both sides by 1 minus r. And we have the formula. This should be the formula on your card. So first term, common ratio, and that is the formula for a geometric series, a finite geometric series, meaning there is a final n or number of terms. On your card, I can't remember if you have both of them or not. I know that you don't have this. You may write this. Yes, I'm saying you may write this on your card. So we use this formula when r is less than 1. We use this formula when r is bigger than 1. Actually, you can use this one for everything. That's really what I do. But some people freak out if r is bigger than 1, because then when you subtract, you get a negative number. But you end up with a negative number over a negative number. They cancel out. No big deal. So if you want to memorize both and not have to worry about a negative number, go ahead. If you only want to memorize one, you can use this one every time. I'm about to cough, so you might want to turn the volume down. Sorry about that. Okay, find the sum of the first six terms of the geometric sequence with first term 5 and constant ratio. So we ask ourselves, self, sequence or series? It says sum, so series. Next term, arithmetic or geometric? Well, this one was easy because it says geometric. Okay, so what's the first term? 5. What's the constant ratio? It's covered up. Let's find it. -4/3. So the first 6 terms, so n is 6. S sub n equals, go back and look, we're going to go 1 minus r to the n over 1 minus r. So g sub 1, 5 times 1 minus r, so -4/3 to the n, 6 over 1 minus a -4/3. Let me go back and double check. Got it. Okay, 5 times 1 minus, when you take -4/3 to the 6th, I will reach for my calculator. Let's hope I have batteries. Whoa! And as I leaned, you can see my tablet fell on my keyboard, so let's go find out where we are. This looks like the end. Too bad I can't pause or edit. That would be nice. Really? Oh, because it's still going the other way. Well, you work this out while I get back to the screen I was on, because now it's making new screens. Gotta love technology. There we go. Hopefully it's done being weird. Let's go find out where we were. Hey, this isn't any different than being in class, is it? Okay, we're way past that. We're past that. We're way past that. Oh, I'm glad I hit this one. Put some of these down for you to check if you want to do extra examples. I believe they're from 8.2. Okay, we're almost there. All right. So, hopefully you worked on this while I was getting my calculator. Okay, so we need -4 divided by 3 to the 6th power. And we have 4096 over 729 over 1 plus 4/3. I think I'll extend this page. Okay, let's keep doing the algebra. I'm going to go the long way a little bit. I'm going to call this 729 over 729 minus 4096 over 729, and then the whole thing is over 3/3 plus 4/3 is 7/3. Dividing by a fraction, I'm going to turn the bottom one upside down. Multiply by the reciprocal, times 5, times 729 minus 4096. 729 minus 4096. Negative 3367 over 729. Three times 5 is 15. 15 times 7 over 7, sorry, times negative 3367 over 729. I got negative 2405 over 243. If the fraction freaks you out, let's get a decimal. Negative 9.897. By the way, I chose to stop here because it was 119, so a 1 after that is pretty much of a drop off. Okay, so once again, we found out it was a series because it said sum. It said it was geometric. The first term was 5. The constant ratio was -4 over 3. The n was 6. We plugged it into the formula, took our fraction to the 6th power, did simple arithmetic, not even algebra because there's no variable, and I got negative 9.897. Let's go over that, stop and go over it if you need to. Here we go. Find the sum of the geometric series. Okay, it is a geometric series. Let's identify the first term is 180. How do we find the next term? 90 divided by 180 is 1/2. 45 divided by 90 is 1/2. So R is 1/2. Now, we need to know what n is. We do not know what n is. So, we're going to put this in the explicit formula for a geometric sequence. G sub n equals first term 180 times R, which is 1/2, to the n minus 1. Check that with your formula on the card. Let's find out what that is. Well, this is 4532. It equals 180 times 1/2 to the n minus 1. If we'd studied logarithms already, we could divide by 180 and then take the log of both sides and get n by itself. Feel free to do that. It's actually next chapter. But since we haven't, you can see I've started my calculator. And as soon as it starts up, we'll type it in. Again, I'm sorry I don't have pause here. So we are going to graph this. we're going to graph our fraction. So 45 divided by 32, a little bit bigger than 1. And then we're going to graph, oh, I have a plot turned on. Go up and turn that off. 180 and then times 1/2 to the x minus 1. Okay, well, for my window, I know my y's need to be not very high. I'll go 0 to 20. I really don't know what this will be. But my y's need to go 0 to about 1.5. By the way, my dog is looking out the back window, and she may decide to bark, as she just did. So, you might hear her bark here in a second. I'll change that to 2. Delete that. Meet my dog, Lola. Okay, let's graph it. And there goes the 45 over 32. Here comes the graph of exponential decay coming in. Let's find out where it crosses. Intersect. It's now on the straight line, and you can see the equation up here. I hit enter again, and it goes to the curved line. I identify, yep, that's my other curve. Now let's go left arrow back pretty close to where the intersection is. In other words, hey calculator, start looking here. At 8, so n equals 8, we have that number. So n equals 8. That's our solution. We'll see if we can pull this over and put it up here for now. Okay. So before my dog starts barking like crazy, let's get the sequence in. So we want the series. There's so many S words. And we found out n is 8, so S sub 8, and that equals G sub 1, which is 180, times 1 minus 1/2 to the 8th over 1 minus 1/2. Let's see, 1, that's 180, times, I should know what 2 to the 8th is, 256. So 1 minus 1 over 256 over 1 minus 1/2. Simplify 180. Call this 256 over 256. Subtract 1 256 from 256. I get 255 over 256. 1 minus 1/2 is 1/2. So 180 times 255 over 256 times 2 equals 360 times 255 over 256. I immediately know, in case I type something in my calculator, that these numbers are going to be pretty close. To 360, just a tad bit underneath it. Okay, let's plug it in. Get back to a regular screen. We have 360 times 255 divided by 256. And the answer is 358.59375. I'll write it down here. I'll just drag it. Slide it up there. All right, let's get the next example. So now you have a sigma question. We can identify a few things. Hopefully you recognize this as the geometric sequence explicit formula. So we know right away this is our G sub 1. We know right away this is our R. We had to use I here because these two variables should match. So you could, it's just 7 of them, you could find the first 7 terms and add them together, or you can use the formula for a series. 7 terms of a series, 7th partial series, 7th partial sum. You do 7 over 2. Oh, hello, wrong formula. Went back to arithmetic. G sub 1, which is 18 times 1 minus 1/3 to the 7th over 1 minus 1/3. 3 to the 7th. $21.87. So this is 18 times 1 minus 1 over 21.87. 1 minus 1/3 is 2/3. 18 times, call 1 21.87 over 21.87. Subtract 1, you get 21.86 over 21.87. We're multiplying by 2, or dividing by 2/3, so let's multiply by 3 over 2. Do a little canceling. 2 goes into 2 once, 2 goes into 18 9 times. 9 times, 3. I'll write it out. Times 3 times 21.86 over 21.87. That's 27 times 21.86 over 21.87, which you see is just going to be just about 27. So I go 27 times 21.86 divided by 21.87. And I get 21.86 over 81. Obviously 27 went into that. And as a decimal, that is 26.988 because it was 876. Let's go to the next one. Ball bounce problems. Get used to this. They're going to happen a lot. So let's get a picture of what's going on here. The ball bounces 2/3 of the height from which it falls. What is the total distance the ball travels from the time it's dropped from a height of 12 feet to the moment it hits the ground for the 6th time? Starts up here, hits the ground, comes back to 2/3, hits the ground. It actually is going straight up and down, but I'm drawing it over time. Comes up 2/3, 2/3. What do we know about this? We know this distance is 12 feet. It just flat went 12 feet. So this is 2/3 12 feet. 2/3 times 12 is 8. 2/3 times 8, punch it in to find out. What's the total distance it's dropped from a height of 12 feet to the moment it hits the ground for the 6th time? Okay, let's count how often it hits the ground. There's 1, there's 2, there's 3, there's 4, there's 5, and then it goes up one more time and hits 6. Let me move all these up a little bit. Okay, so by the time it hits the ground, now let's get kind of in our minds a general way for dealing with these because we're going to deal with a lot of them. Okay, the total distance the ball travels from the time it's dropped to the moment it hits the ground for the 6th time. So notice, how many terms do we have here? If you count this as G sub 1, then it hits 2, then 2, 3, then 3, 4, then 4, 5, then 5. So this is G sub 6. That's your 6th term. 1st term, 2nd term, 3rd term, 4th term, 5th term, 6th term. Let's get a pattern. So when it's going to hit the ground the 6th time, that's the 6th thing. Notice one other thing. Every time it goes up, it comes down. Imagine that, gravity. So except for the first time, it drops in the first time. So we have one length of 12, two lengths of 8, two lengths of whatever this is, two of that, two of that, two of that. Here's the way I propose we do it. So we want the sixth sum, so we want S sub 6. But we need to multiply it times 2 because it went up and down each time, but we need to subtract the first term, G sub 1, because it only came down from there. So let's use this general formula and let's put everything inside. I'm going to replace G sub 6 with the formula for it. So the first term, which was 12, times 1 minus 2/3 to the 6th power over 1 minus 2/3 minus the first term, which is 12. Okay, let's simplify this in here. 1 minus, well, 2/3 to the 6th, 2 to the 6th over 3 to the 6th. So we get on the top, well, 12 times 1 minus 64 over 729. 1 minus 2/3 is 1/3. Minus 12. Next step, 1, so 729 over 729 minus 64 is 729, so 729 minus 64. So this becomes 665 over 729. Since we are dividing by 1/3, we're going to multiply by 3 over 1. Not sure why I left room for the fraction. Then close the parentheses, minus 12. Now we're multiplying here, so I can just start combining that. 12 times 3, well, let's do this. 2 times 12 is 24 times 3. 72, 2 times 12 times 3. 72 times 665 over 729 minus 12. $43, 48, 81. And a decimal approximation, 53, 679. There's a 0 after that, so we'll leave it at 9. We are talking about feet, so it will have traveled a little more than 53.5 feet. Go back, look at this equation. Make sure it makes sense with the diagram that you have drawn. Draw it in there. We're going to have lots of these problems. And I'll move on. A golf ball is dropped from a height of 81 yards. See, I told you we would have a lot of these. Okay, the golf ball is dropped 81 yards. There's your 81. Rebounds 3/5 of the distance. Now let's start getting some questions. How high does it rise on the 7th bounce? On the 7th bounce. That's one term of a sequence. So we're talking about, hello, wrong ink. A sequence. The first term on how high does it rise on the 7th bounce. We're going to consider this to be after. Remember, go back to the last one and notice that the 7th term comes before the 7th bounce, so you really need the 8th term. So we need G sub 8. What is that? That's the first term 81 yards times r, so 3/5 to the 8 minus 1 power. Hey, when you're doing series, we've been putting just the n up here. Remember, for sequence, it's n minus 1. Okay, I'm just going to type this in my calc. 81, whoops, maybe, 81 times, parentheses, 3 divided by 5, close my parentheses, to the 7th power. And I have a very nice fraction of 177,147 over 78,125. That decimal approximation is about 2.267 yards. So it drops from 81 yards, that's pretty high. It rebounds, and after the 7th bounce, it's the 8th term, which is 2.67 yards. How far will it have traveled when it hits the ground for the 7th time? Now, when it hits for the 7th time, remember that's the 7th term. So we can do S sub 7. But we have to go 2 times that minus the first term, which in this case is 81. So G sub 1, 81 times 1 minus 3/5 to the 7th bounce over 1 minus 3/5. Well, I got 3/5 to the 7th. Oh, that was 81 times it, so I don't. Three-fifths to the 7th power. So 81 times 1 minus 2187 over 78,125. 1 minus 3/5. 5/5 minus 3/5 is 2/5. So we have 81 times 78,125 minus, well, 78,125 over 78,125 minus 2,187 over 78,125. So I subtract the numerators. 78, I might as well just use the calculator here. So 78,125 minus 2,187. Good thing we have good calculators. 75,938. 75,928 over 78,125. Let me go check that value. 938. And then we're going to multiply by 5 over 2. So in my calculator, 81 times 75,938 divided by 78,125, then times 5 divided by 2, 196.83. We'll just stop there at 83 yards. So it's dropped at 81. By the time it hits the ground the 7th time, it's gone up and down 6 times, dropped at 81. Oh, still have to subtract my 81, don't I? 115.83 yards. Okay, again, make sure you go over this. Make sure you can repeat this because you can see it's going to happen a lot. A virus enters a community and the number of new infections each week forms a geometric sequence. Assume the first week there are 14 cases, so this is G sub 1. Each week thereafter the number of new infections increases by that, so R is 1.25 because it grows by that. Use sigma notation to express the number of people infected by the nth week. So we're going to do sigma, we're going to go to n, we're going to start with 1, and we're going to use explicit formula here. So first term, which is 14, times the ratio 1.25 to the n minus 1. This is the explicit formula for a geometric sequence. Putting the sigma here sums that sequence, so now we have a series. How many people have the disease by end of the 5th week? S sub 5. 14 is our first term. And you could plug it in, put sigma in there, 5 and 5. We're going to go 1 minus 1.25 to the 5th. 1 minus 1.25. You might remember that I said there was another formula where it switched. It would have r to the n minus 1, an r here minus 1 for when r is bigger than 1. But I told you I keep the same, so I only have to memorize one formula. So that's what I'm doing. So 1 minus, I'll show you here that it works either way. 1.25 to the 5th. 3.0516. 1 minus blah blah blah, that takes it to negative 0.25. In my calculator, I'm going to keep the decimal, so 14 times 1 minus, use that number, so answer, and then divided by negative 0.25. And I got 114.898 people, right? How many people? Now, you could say, do you round it to 115? They haven't quite gotten that yet. Do you drop it to 114? Or you just say this is a statistic. And it should be about 114.898 people. Always put context on these answers, so use your words to say what you're going to use here. These are additional examples. Feel free to go back over them, pause and look. There's Stephen's solution to something from last year. And that ends the lesson. This is long enough. I'm signing off. Go back and watch anything you need to watch.